Something strange has appeared in nearly every deep-field image of the early universe. Tiny crimson objects, scattered across the oldest regions of space ever observed. Everywhere the James Webb Space Telescope looks, they seem to be there. Astronomers call them little red dots, and right now, nobody fully understands what they are. The deeper scientists investigate these objects, the more unsettling they become. Because, according to everything we know about the early universe, objects this ancient should still be primitive, small collections of gas and stars slowly assembling over time. But these aren't small. They're extraordinarily compact, unbelievably bright, and far more massive than they have any right to be at such an early stage of cosmic history. Some researchers now believe we may be looking at something entirely new. Not quite a galaxy, not quite a black hole, possibly a completely unknown class of cosmic object, something behaving like both at once. If that sounds impossible, that's because it might be. But if these little red dots are real, they could help solve one of the biggest mysteries in modern astrophysics: how supermassive black holes formed so quickly after the Big Bang. Since its launch on December 25, 2021, the James Webb Space Telescope has transformed our view of the universe. Webb has already completed tens of thousands of hours of observations and returned hundreds of terabytes of data from the deepest regions of space ever explored. And hidden inside those observations, one type of object keeps appearing again and again. The first hints emerged during deep field surveys like EAGER and FRESCO, projects specifically designed to study galaxies forming within the universe's first billion years. Webb was peering back to a time only a few 100 million years after the Big Bang, expecting to see faint, chaotic proto-galaxies slowly taking shape. Instead, astronomers found these strange red objects everywhere. By around 600 million years after the Big Bang, the universe appears crowded with them. Then, strangely, they almost completely vanish later in cosmic history. That alone makes them extraordinary. So what do we actually know about them? For one thing, they're tiny on galactic scales, usually less than 500 light-years across, hundreds of times smaller than the Milky Way. Yet despite their small size, they shine with incredible intensity, and they are extremely red. Not just red because of cosmic expansion, but red in a way that standard models struggle to explain. For years, telescopes like Hubble Space Telescope simply couldn't see them properly. Their light had been stretched so deeply into infrared wavelengths by the expanding universe that only Webb's instruments were sensitive enough to detect them clearly. When astronomers finally analyzed their spectra in detail, things became even stranger. Normally, the farther away an object is, the redder it appears due to redshift, the stretching of light as space itself expands. But with the little red dots, ordinary redshift wasn't enough to explain what Webb was seeing. Something else was happening. At first, researchers suspected dust. Cosmic dust scatters blue light more efficiently than red light, making distant objects appear redder, similar to how Earth's atmosphere turns sunsets orange and crimson. A heavily dust-obscured galaxy packed with intense star formations seemed like a reasonable explanation. But when Webb's near-infrared spectrographs split their light into detailed spectra, the pattern didn't match anything astronomers expected. The objects emitted strong ultraviolet and blue light, strong infrared and red light, but comparatively little in between. The result was a bizarre V-shaped spectral signature unlike almost anything previously observed in the early universe. Then scientists noticed another clue. At a wavelength of 364.6 nanometers, the spectrum suddenly changed sharply, a feature known as a Balmer break, typically associated with large populations of hot young stars. At first, this seemed promising. Maybe the little red dots were simply extreme starburst galaxies, compact systems rapidly forming enormous numbers of stars. That explanation checked several boxes at once. Young stars could explain the Balmer signature. Dense stellar populations could explain the brightness, and thick dust clouds could explain the redness. For a moment, it looked like the mystery might already be solved. Then the calculations failed. The numbers simply didn't make sense. To produce that much light in such a tiny region, These objects would need impossibly large numbers of stars packed together at densities far beyond anything known in normal galaxies. The early universe shouldn't have had enough time to build structures like this. And suddenly, the little red dots stopped looking like unusual galaxies and started looking like something entirely different. Researchers soon realized they were facing two enormous problems. The first problem was dust. At first glance, dust seemed like the perfect explanation for why the little red dots appeared so unusually red. Cosmic dust absorbs and scatters shorter blue wavelengths while allowing longer red wavelengths to pass through, naturally tinting distant objects crimson. But there was a catch. Dust has to come from somewhere. In galaxies, dust is primarily created by stars, especially massive stars that explode as supernovae. And astronomers already understand the relationship between stellar populations and dust production remarkably well. So in late 2024, astronomer Caitlin Casey and her team attempted to estimate how many stars these little red dots should contain based on the optical light web detected. Then they calculated how much dust those stars could realistically produce. The result was shocking. Their models produced only about 1% of the dust required to explain the extreme redness of these objects. A discrepancy that large is catastrophic in astrophysics. It meant one of two things had to be true. Either our understanding of how dust forms in galaxies is fundamentally wrong. The primary source of light inside the little red dots isn't starlight at all. Then came the second problem: brightness. To explain the luminosity of these objects using stars alone, astronomers would need to pack absurd numbers of stars into an incredibly tiny region of space. The densities quickly became physically unreasonable. In some models, stars would need to sit only a few astronomical units apart, closer together than many stars are in real stellar clusters. At those distances, stars wouldn't remain stable for long. They would constantly, gravitationally disturb one another, collide, merge, and trigger chaotic chain reactions. The systems simply shouldn't survive. And there was something else strange. The little red dots didn't look like galaxies. Normally, even distant galaxies show at least some faint internal structure: a disk, a glow, irregular clumps of star formation. But despite the extraordinary resolution of the James Webb Space Telescope, these objects often appeared as single unresolved points of light. Like stars. That suggested two possibilities. Either the objects were unbelievably compact, or their light was dominated by one incredibly bright central source powerful enough to drown out everything surrounding it. Which led astronomers to a second theory. What if the little red dots weren't star-filled galaxies at all? What if they were powered by black holes? That idea immediately solved several problems at once. At the centers of most galaxies sit supermassive black holes surrounded by accretion disks, swirling rings of gas and dust falling inward under immense gravity. As material spirals toward the black hole, it becomes compressed and heated to extraordinary temperatures, glowing with tremendous intensity. Active black holes are among the brightest objects in the universe. Surrounding many of these accretion disks is a thick donut-shaped cloud of gas and dust called a torus. Viewed from the side, that torus blocks shorter wavelengths of light while allowing red and infrared wavelengths to escape more easily, which sounded extremely familiar. The black hole model explained the redness. It explained the brightness. It explained why the objects appeared point-like. And then astronomers found another clue supporting the idea. The spectra of the little red dots showed broad Balmer lines, signatures produced when gas moves at enormous speeds around a compact central object. Here's why that matters. Gas orbiting a black hole travels thousands of kilometers per second. Some of that gas moves toward us, causing its light to shift slightly blue. Some moves away, shifting its light red. Together, those motions stretch the spectral lines outward, broadening them dramatically. The faster the gas moves, the broader the lines become. And Webb was seeing exactly that kind of broadening. For a while, the black hole explanation looked incredibly promising. Then researchers noticed something devastating. The little red dots weren't emitting X-rays. As far as we understand modern astrophysics, actively feeding black holes should produce powerful X-ray radiation from the hottest regions closest to the accretion disk. But when astronomers searched for X-rays from the little red dots, they found almost nothing. That absence created a major problem for the black hole interpretation. And then came yet another mystery. The black holes appeared far too massive for the galaxies surrounding them. In the modern universe, supermassive black holes typically contain about 0.1% of the total mass of their host galaxy. This relationship is so consistent that astronomers believe galaxies and black holes must somehow evolve together, regulating each other through feedback processes over cosmic time. But the little red dots completely broke that pattern. Some estimates suggested black holes making up closer to 10% of the total galactic mass. It was as though the black hole had somehow grown first, while the galaxy itself lagged far behind. Astrophysicist Fabio Picucci summarized the dilemma perfectly. If these objects contain black holes, the black holes are absurdly overgrown for such tiny galaxies. But if they contain only stars, the galaxies are impossibly compact. Neither explanation fully works, and that leaves astronomers facing a deeply uncomfortable possibility. What if the little red dots are not merely unusual versions of things we already know, but an entirely new kind of cosmic object? This was the mystery that astrophysicist Anna de Graaf and her team set out to solve. De Graaf specializes in the strangest objects in the early universe, the rare outliers that refuse to fit neatly inside existing models of cosmology. So instead of waiting for these mysterious objects to appear by chance, her team decided to hunt for them directly. The project became known as the Rubies Survey, short for Red Unknowns, bright infrared extragalactic sources, and its mission was simple: search the deepest regions of space for the reddest, brightest, and most unusual objects Webb could possibly detect. Throughout 2024, the team spent nearly 60 hours using the James Webb Space Telescope to collect detailed spectra from around 300 extremely red sources scattered across the distant universe. Among them, researchers believe roughly 30 to 50 were the mysterious little red dots. At the time of publication in March 2025, it became the largest spectroscopic study of little red dots ever conducted. And the objects themselves were astonishingly ancient. Some existed just 650 million years after the Big Bang. Others appeared roughly 1.5 billion years after cosmic dawn. These were not nearby galaxies. They were relics from the universe's earliest chapters. But instead of bringing clarity, the survey made the mystery even worse. Because the deeper scientists looked, the less these objects resembled a single category of cosmic structure. At first glance, many of the little red dots looked nearly identical: tiny, bright, deeply red. But spectroscopy revealed they were far more diverse than anyone expected. Some appeared to be dusty galaxies still actively forming stars. Others looked like galaxies that had somehow shut down star formation shockingly early, and some clearly showed signs of actively feeding supermassive black holes buried at their centers. In other words, both major theories seemed partially correct. The starburst galaxy camp wasn't entirely wrong. Neither was the black hole camp, but buried within the survey was a smaller subset of objects that fit neither explanation properly. These were the truly strange ones. The objects with the bizarre V-shaped spectra, the broad emission lines, the point-like appearance, the exact same features that had resisted explanation from the very beginning. Then, in July 2024, the team found one that stood out even among the anomalies. A little red dot nearly 11.9 billion light-years away with a spectrum so extreme it immediately captured the attention of the entire team. They called it the cliff. And to understand why the cliff mattered so much, you first need to understand what a Balmer break actually is. Imagine electrons orbiting an atom like rungs on a ladder. They cannot exist at arbitrary energies, only at very specific levels. When a photon arrives, carrying exactly the right amount of energy, it can push an electron upward to a higher level. In that process, the photon itself is absorbed. Because every element has a unique electron structure, each one absorbs very specific wavelengths of light. That's why spectroscopy works so well. Every atom leaves behind its own fingerprint. For hydrogen, one of the most important thresholds occurs at 364.6 nanometers. Below that wavelength, photons carry enough energy to completely ionize hydrogen atoms from a particular energy state. Those photons get absorbed. Longer wavelengths don't carry enough energy, so they pass through relatively unhindered. The result is something astronomers call a Balmer break, a sudden drop in brightness across a specific part of the spectrum. In ordinary galaxies, this break usually appears soft and gradual because the light is passing through messy mixtures of stars, dust, clouds, and gases of varying temperatures and densities. But the cliff was different. Its Balmer break was almost vertical, sharp, clean, extreme. In fact, the break appeared roughly twice as strong as anything previously observed from ancient cosmic objects, which immediately suggested something bizarre was happening. The sharper the Balmer break, the more uniform and hydrogen-rich the surrounding environment appears to be, and that created a contradiction, because the same spectra that implied an enormous cloud of hydrogen also appeared to show evidence for a rapidly feeding supermassive black hole hidden at the center. One signal pointed toward a black hole, the other looked almost star-like. It was as though the object was somehow behaving like both at once. That possibility pushed researchers toward an idea that sounds almost impossible: a completely new type of cosmic object. De Graaf proposed the term black hole star. The idea is extraordinary. A black hole star would resemble a gigantic star from the outside, wrapped inside an immense sphere of hot hydrogen gas. But unlike ordinary stars, it wouldn't be powered by nuclear fusion in its core. Instead, the energy source would be a supermassive black hole rapidly devouring matter at the center, converting gravitational energy into light. Essentially, a black hole disguised as a star. And strangely enough, that idea could explain several mysteries simultaneously. It could explain the brightness, the compact appearance, the broad spectral lines, even the massive hydrogen envelope surrounding the object. But enormous questions still remain. Where did all that hydrogen come from? Why don't these objects emit strong X-rays like normal active black holes? And perhaps most importantly, how could something like this even form in the early universe? To answer that, scientists turn towards something even stranger: dark matter halos. Modern cosmology suggests galaxies form inside enormous invisible structures made of dark matter, massive gravitational scaffolds, woven throughout the universe like a gigantic cosmic web. We cannot see these halos directly, but through gravitational lensing, astronomers can map their influence. And intriguingly, the structure of this web resembles enormous interconnected neural networks stretching across space. Most dark matter halos rotate relatively quickly. That spin causes gas to spread outward as galaxies form, similar to how a spinning carnival ride pushes riders away from the center. But a tiny fraction of halos appear to rotate extremely slowly, and inside these rare low-spin halos, something remarkable may happen. Instead of spreading outward as galaxies normally do, the gas remains trapped, dense, compact, and incredibly concentrated. In environments like these, astronomers believe the first black hole stars could begin to form. The idea is simple in principle, but astonishing in implication. A young black hole forms at the center of a massive hydrogen cloud. But unlike ordinary black holes, the surrounding gas doesn't disperse. It stays bound around the object, creating an enormous envelope of dense hydrogen capable of producing the strange properties we observe in the little red dots. And that may finally explain one of the biggest mysteries of all: the missing X-rays. Because, according to the black hole star model, the X-rays were never absent in the first place. They were trapped. The hydrogen envelope surrounding the black hole would be so thick and opaque that even extremely energetic X-ray radiation couldn't escape directly into space. Instead, those photons would slam into surrounding gas particles over and over again, losing energy with each interaction. Eventually, the energy would be re-emitted as lower-energy thermal radiation, producing the intense red and infrared glow Webb actually detects. In other words, the object hides its own black hole behind a cocoon of gas. But the theory becomes even more compelling when you examine the remaining mysteries surrounding the little red dots. The bizarre V-shaped spectra, the apparent lack of dust, the impossibly oversized black holes. One by one, the black hole star model seems capable of addressing all of them. Astronomer Rohan Naidu and his collaborators explored exactly this possibility in 2025 while studying another object they believed behaved like a black hole star. Their observations revealed an enormous hydrogen envelope nearly 40 astronomical units across, wider than the orbit of Pluto, along with one of the strongest Balmer breaks ever observed anywhere in the universe. Naidu proposed that black hole stars are actually two-component systems. At the center sits the black hole star itself, compact, bright, and buried inside dense hydrogen gas. This component produces the broad emission lines, strong red glow, compact point source appearance, and dramatic Balmer break. But surrounding that object is a larger host galaxy still actively forming stars. That outer galaxy contributes narrow ultraviolet emission lines produced by hot young stars. When both signals combine together, they naturally create the bizarre V-shaped spectral energy distribution astronomers see in the little red dots. Suddenly, the strange spectrum stops looking impossible. It becomes the combined fingerprint of two overlapping cosmic structures. And the model also solves the dust problem. Under traditional galaxy theories, astronomers needed enormous quantities of cosmic dust to explain why the little red dots appeared so red. But calculations repeatedly showed there simply wasn't enough dust available in such young galaxies. The black hole star model removes that problem entirely. The redness doesn't come from dust at all. It comes from radiation struggling to escape through the dense hydrogen envelope surrounding the black hole itself. No missing dust, no contradiction. Then there's the issue of the overmassive black holes. At first, researchers believed the black holes inside little red dots were absurdly large compared to the galaxies surrounding them, sometimes approaching nearly 10% of the galaxy's total mass instead of the normal 0.1% observed nearby. But black hole stars may distort those measurements too. Normally, astronomers estimate black hole mass by measuring how broad certain emission lines appear inside the spectrum. Faster-moving gas creates broader lines, implying stronger gravity and therefore a larger black hole. But inside a black hole star, photons don't travel freely outward. They bounce repeatedly through the thick hydrogen envelope, scattering again and again before finally escaping into space. Each interaction slightly alters the photon's wavelength, and collectively, those countless interactions artificially broaden the spectral lines. The result? The black hole only appears far larger than it really is. Once researchers corrected for this effect, the estimated masses dropped dramatically, bringing them much closer to the expected ratios seen in ordinary galaxies. Which means black hole stars may elegantly solve nearly every major problem associated with the little red dots. And perhaps the strangest part of all this, the idea may have been predicted long before Webb ever launched. Back in 2008, theoretical astrophysicist Mitchell Beagelman proposed a hypothetical object known as a quasi-star. Beagelman imagined a black hole forming inside a gigantic cloud of gas shortly after the Big Bang. Instead of dispersing, the surrounding envelope would remain gravitationally bound around the growing black hole. The black hole would feed continuously from the inside, while the outer gas shell radiated enormous amounts of light. From a distance, it would resemble a gigantic star, but at its core, it would actually be a rapidly growing black hole. A black hole disguised as a star. Exactly the kind of object astronomers may now be seeing with the James Webb Space Telescope. Beagelman's calculations suggested these quasi-stars could grow extraordinarily fast, reaching thousands of solar masses within only a few million years while the surrounding envelope gradually cooled. And if objects like these truly existed in the infant universe, they may finally explain one of cosmology's oldest mysteries. Supermassive black holes appeared so impossibly early after the Big Bang. Eventually, the envelope surrounding the quasi-star cools to a critical threshold, roughly 4,000 Kelvin. And at that point, everything changes. The outward pressure from radiation finally overpowers gravity. The enormous hydrogen shell is blown away into space. The quasi-star phase ends. and what remains behind is a newly exposed black hole. According to Mitchell-Bagelman, quasi-stars may never have been permanent objects at all. Instead, they could represent a brief but critical phase in the early life of certain black holes, a transitional state lasting only a few million years before the surrounding gas disperses completely. But Begelman proposed something even more intriguing. If a black hole later encountered another period of extremely intense gas inflow, the same conditions might arise again. In theory, a black hole could pass through multiple quasi-star-like phases across its lifetime, and that possibility may explain one of the strangest features of the little red dots themselves. They disappear. By roughly 1.5 billion years after the Big Bang, the population of little red dots seems to vanish almost entirely from the observable universe. Perhaps the reason is simple. The early universe was uniquely chaotic, flooded with dense primordial hydrogen clouds capable of feeding black holes at extraordinary rates. As cosmic time progressed, those perfect conditions gradually disappeared. The universe changed, and the little red dots disappeared with it. Which raises an astonishing possibility. Could the James Webb Space Telescope now be observationally confirming ideas Begelman proposed nearly 2 decades ago? Possibly, but the field remains deeply uncertain. Research into little red dots is moving at extraordinary speed. Hundreds of papers have appeared within just the last 2 years alone, with new interpretations emerging faster than many researchers can fully absorb them. For now, the black hole star model appears to fit the available evidence better than any competing explanation. But it is far from confirmed. Major questions still remain unanswered. How common are black hole stars? How long does the phase actually last? What triggers it? What determines when the hydrogen envelope forms? And when it finally disperses? At the moment, the life cycle of a black hole star remains almost entirely unmapped. Yet what makes the little red dots truly important extends far beyond the mystery itself, because they may hold the key to one of the biggest unsolved problems in all of astrophysics: the origin of supermassive black holes. We know enormous black holes exist at the centers of most large galaxies, including the Milky Way itself. We also know that some of these objects had already reached billions of solar masses only a few hundred million years after the Big Bang, and according to conventional growth models, that should be impossible. Under normal stellar collapse scenarios, early black holes should have remained relatively small during that period, perhaps only 10 to 100 solar masses. There simply shouldn't have been enough time for them to grow so enormous so quickly. The black hole star model potentially eases that tension in 2 different ways. First, the broad spectral lines used to estimate black hole masses may be artificially exaggerated by photon scattering inside the dense hydrogen envelope. If that's true, many early black holes may not be quite as massive as they initially appeared. But the second possibility is even more important. Black holes may be capable of growing much faster than physicists once believed. Normally, black hole growth is restricted by something called the Eddington limit, a balance point where the outward pressure from radiation pushes back against infalling matter, limiting how rapidly the black hole can feed. But inside a black hole star, the surrounding hydrogen envelope fundamentally changes the physics, because the radiation pressure is no longer determined solely by the black hole itself. Instead, it becomes distributed across the entire massive gas envelope surrounding it, and that could allow black holes to feed at rates far beyond the traditional Eddington limit. In other words, black hole stars may provide exactly the kind of extreme environment needed for supermassive black holes to grow extraordinarily fast in the infant universe. But another mystery still lingers beneath all of this. Where did the original black holes come from in the first place? So far, the only black hole formation pathway humanity has directly observed comes from collapsing stars. But the little red dots appear far too early and far too massive for ordinary stellar semnants to explain them adequately. Which leads to another possibility. Perhaps some black holes formed directly from enormous primordial gas clouds shortly after the Big Bang, bypassing normal star formation entirely. These hypothetical objects are known as direct collapse black holes. For decades, they've existed only as theoretical models. But the little red dots may represent the first real observational evidence that such objects actually formed in the early universe. Right now, astronomers are still focused on understanding the fundamentals, measuring temperatures, luminosities, spectral properties, trying to construct something equivalent to a stellar life cycle diagram, but for black hole stars. Because remarkably, humanity has never truly had one, and the little red dots may finally allow us to build it. Ultimately, this is how science moves forward, not by protecting old ideas, but by challenging them. Sometimes a single discovery forces entire frameworks to be reconsidered, entire textbooks rewritten, decades of assumptions revisited from the ground up. And if that process brings us even slightly closer to understanding the true nature of the universe, then the upheaval is worth it. Thanks for watching.